We're now going to consider a macroscopic system, and since we have found out that it's very important to count the accessible number of states for a given value of a parameter in order to determine its mean value and probabilities, this is a very important discussion. So let's say that we have a macroscopic system with external parameters so that we know its energy levels. Okay, so we have a macroscopic system with given external constraints so that its energy levels are determined. So you can recall, for example, our spin system that is placed in an external magnetic field. If the system is isolated, for example, its total energy can be fixed to be, let's say, minus 2 mu 0 b, etc., where b is the external magnetic field and mu 0 is the magnetic moment per spin. So the situation is similar to that. We have any macroscopic system with external constraints, and so we know the energy levels because the energy levels, if you recall, are determined by these external constraints, like the magnetic field, for example, for the spin system. So we're going to define a few items here, and this is going to be very important to understand what these items refer to. So first of all, capital E is the total energy of the system. And remember, the total energy of the system is fixed if the system is isolated. And next we have omega as a function of E. This is the number of accessible states which correspond to a total energy for the system in the range E to E plus delta E, where delta E is a macroscopically small energy interval, but microscopically large energy interval. And we call rho as a function of E the number of states you can have per unit energy range. And this is something that changes as a function of energy. So this is at the given energy. There is a very good name for rho. It's called density of states, or in short we can call it DOS, density of states. We call capital letter phi as a function of E the total number of states with energies for which the energy of the system will be less than E, and we call F the number of degrees of freedom and recall that this is the number of values we can have for all possible quantum numbers. For example, for a one-dimensional box with a single particle, we had one quantum number n. So the number of degrees of freedom would be 1, because you have to specify only one quantum number. For a three-dimensional box, you have to specify nx, ny, nz, three quantum numbers. F is 3. For capital N particles in a three-dimensional box, you have to specify those three values, nx, ny, nz, for all particles separately. So you have number of degrees of freedom 3n. So for a macroscopic system, this is of the order of Avogadro's number. So that's like 10 to 24 set of quantum numbers you have to specify in order to get the state of the quantum state of this system. Epsilon is the contribution to the total energy of the system E from each quantum number and then we have lowercase phi as a function of epsilon is the total number of possible values of a quantum number when its associated energy is less than epsilon. We call E0 the ground state energy, ground state total energy. We call epsilon 0 minimum possible contribution, to the total energy E from a quantum number. Okay, so these definitions are very important. So once again, we can repeat. We call E the total energy of the system. When the total energy of the system is E, there is a certain number of accessible states for the system, and this is for the system being with a total energy in a range E to E plus delta E, where delta E is a macroscopically small energy interval, but macroscopically large. Rho as a function of E is the number of states per unit energy range at the given energy E. It's called density of states. Capital phi is the total number of states with energies less than E. F is the number of degrees of freedom. It's the number of quantum numbers you have to specify in order to get the state of the system. Epsilon is the contribution to total energy E from each quantum number. Lowercase phi as a function of epsilon is the total number of possible values of a quantum number when its associated energy is less than epsilon. E0 is ground state energy, and epsilon 0 is the minimum possible contribution to the total energy from a given quantum number. So because we know the number of states per unit energy at energy level E, we can write the total number of accessible states for energies in the range E to E plus delta E is the density of states multiplied by that energy interval. So the number of accessible states at energy E is density of states multiplied by that energy interval. Well, where does this come from? Well, basically, if you plot density of states as a function of energy, rho as a function of energy, let's say that it looks like this. It increases with energy like this. Now I pick an energy range E and a very small interval delta E, so E plus delta E. Now you can see that for all practical purposes the density of states here is fixed. It is not changing very much, therefore we use the value at energy level E, because rho at E is almost the same as rho at E plus delta E. So we can just use rho of E multiplied by delta E in order to get the number of accessible states with energies in the range E to E plus delta E. Okay, so once again, this delta E is macroscopically small energy interval but microscopically large, that is to say, it contains many states. Why do I need this? Because I'm treating this function density of states as a continuous function. The energy interval that I pick, I should not care about the discreteness of the energy levels. I should have enough number of states in that energy range so that I can treat the energy as a continuous variable. So this is basically going to guarantee that E is still a continuous variable to a good approximation. So that's what we're trying to achieve by picking a macroscopically small but microscopically large energy interval. So we basically have the number of states accessible to the system in the energy range E to E plus delta E omega, a smoothly varying function of energy. So that's what we achieve by doing so. Now, what is the density of states? Number of states per unit energy. Well, if I look at the total number of states with energies less than E, that is phi. So if I take the derivative of phi with respect to energy, I will get number of states per energy interval. So this is going to be phi at approximately E plus delta E minus phi at energy E divided by delta E. So what am I doing here? I'm counting the total number of states for energies less than E plus delta E and subtracting the total number of states with energies less than E, so that I get the number of states in that energy interval and divided by the energy interval, and this gives me basically rho. So the density of states. Basically, I have found that the density of states rho is the derivative of the total number of states with energies less than E with respect to the energy E. So that is the definition of density of states. So if I substitute that into the equation 1, let's call this equation 2. So this goes to equation 1. What I will have at the end is the following. uh, the density of the number of accessible states for energies in the range E to E plus delta E is derivative of the total number of states with respect to energy multiplied by the energy interval delta E. Now, the other important point I have to consider here is this lowercase phi, total number of possible values of a quantum number when its associated energy is less than epsilon. Now, what is the total number of possible values of a quantum number when its associated energy is equal to epsilon 0, minimum possible contribution? That is the lowest possible value this quantum number can take. In general, as I allow the system, the contribution to total energy becoming epsilon greater than epsilon 0, the number of possible values I can put to the quantum number n will be increasing. So it increases in the following manner. Phi as a function of epsilon, you can say that increases as epsilon minus epsilon 0 to some power empirically, and that power is of the order of 1. And you have the total number of values the quantum number can have at energy epsilon 0, minimum energy is 1, because this is ground state or minimum value of that quantum number. So let's keep this in mind, that the total number of values the quantum number can have scales with its contribution to the energy of the system epsilon, as epsilon minus epsilon 0 to some power of the order of 1. And if I consider the contribution to the total energy from F quantum numbers, so contribution from F quantum numbers, first of all, let's call this one equation 3 or expression 3, relationship 3. The total number to total energy of the system minus the ground state energy of the system is basically the total number of quantum numbers F multiplied by epsilon minus epsilon 0. So epsilon minus epsilon 0 is the additional energy provided by each quantum number, and I multiply it by the total number of quantum numbers, that is number of degrees of freedom F. I get the total energy difference between E and ground state energy E0. So as I increase the number of degrees of freedom in the system, the contribution from each quantum number being epsilon minus epsilon 0 will have a larger effect on the total energy of the system, because it's F times epsilon minus epsilon 0. And finally, what is the relationship between the number of states with energies less than E and this lowercase phi, total number of possible values of a quantum number when its associated energy is less than epsilon? Okay, so the total number of possible states with energies less than E will be given by the following. You should count the total possible number of values each quantum number can have for a contribution epsilon to the total energy E. So this is for the first quantum number. Now you have for the second quantum number phi of epsilon, the third quantum number phi of epsilon, and you do this F times, because you have F quantum numbers to specify F numbers. So basically you reach the conclusion that the number of accessible and number of states available to the system for a total energies less than E will be the total number of possible values each quantum number can have for an energy contribution epsilon to the power f. So this is our fifth relationship. Now, if I look at my density of states again, rho remember is d phi dE, or let me write this properly, it is d phi dE. The derivative of number of states for energy is less than E with respect to E, so it is the number of states per energy interval. And if you look at relationship number 5, this derivative will be equal to f times phi of epsilon to the power f minus 1 d phi lowercase phi dE. But phi is a function of epsilon. You can see this in relationship number 3. So in order to get d phi dE, you need to get first d phi d epsilon and then d epsilon dE. So you can write this as f phi as a function of epsilon to the power f minus 1 d phi d epsilon, because it's a function of epsilon, and then d epsilon dE. So first of all, what is d epsilon dE? So I look at relationship number 4, and the relationship number 4 tells me d epsilon dE will be equal to 1 over f. Because epsilon minus epsilon 0 is E minus E0 divided by f, so derivative with respect to E gives me 1 over f. So I'm going to plug that here. So I get f times phi of epsilon to the f minus 1 d phi d epsilon times 1 over f. So this f and 1 over f will cancel. And now my question is, what is d phi d epsilon? Well, for that I look at relationship number 3, and relationship number 3 tells me that d phi d epsilon is alpha epsilon minus epsilon 0 to the power alpha minus 1, where alpha is of the order of 1. Okay, so this is alpha times epsilon minus epsilon 0 to alpha minus 1. And on the other hand, what is phi to the power f minus 1? So this is what I'm going to substitute here for d phi d epsilon. And for phi to the power epsilon minus 1, that I can also get from relationship number 3, phi to the power f minus 1, phi to the power f minus 1 is epsilon minus epsilon 0 to the power alpha to the power f minus 1. So I'm going to substitute that result for phi to the power f minus 1 here. Okay, so let's see what I get at the end. I'm going to get for the density of states rho of E is phi to the power f minus 1, so it is epsilon minus epsilon 0 alpha f minus alpha, and then I have d phi d epsilon, it is alpha times epsilon minus epsilon 0 to alpha minus 1, and then the epsilon dE I substituted, I got 1 over f, the f's cancelled. Okay, So this is going to tell me that because alpha is of the order of 1, basically I can neglect this term here, and I'm going to get, so this is almost 1, this is almost, alpha minus 1 is almost 0, so I'm going to get this term, that's going to be 1, and therefore for the density of states I will have epsilon minus epsilon 0. Epsilon minus epsilon 0 is, or I can put this sign here, E minus E0 divided by F, that is epsilon minus epsilon 0, to the power alpha F minus alpha, where alpha is of the order of 1. Okay, so let's go to the total number of accessible states for energies in the range E to E plus delta E. This is, remember, the density of states. It's equal to the density of states multiplied by the energy interval delta E. Therefore, this will be proportional to E minus E0 divided by F to the power alpha F minus alpha. And alpha is of the order of 1. F for a macroscopic system is of the order of Avogadro's number, that is much greater than 1. Therefore, I find that the number of accessible states for this energy range scales as the total energy minus the ground state energy to the power F to a good approximation. Okay, so let's call this relationship number 6. All right, so one thing I would like to note here, if I take this one step further, now I'm going to look at not the number of accessible states, but the natural logarithm of the number of accessible states. This will be equal to f times natural logarithm of E minus E0. So it will be scaling like this. And therefore, you will see that the natural logarithm of the number of accessible states is scaling with f. And basically, this is independent of delta E. Why is it independent of delta E? Because you would have the natural logarithm of delta E coming into play here. So let's think about it. Natural logarithm of delta E coming into play here. But since f is very large, that term is negligible. So it's independent of delta E to a good approximation. Therefore, we can just say the natural logarithm of the number of accessible states at the energy interval E to E plus delta E is scaling with the number of degrees of freedom. And this is true for E not equal to E0. If we are at the ground state energy, right, you would have the natural logarithm blowing up. So that relationship is only valid for an energy, excited state energy of the system. Okay, so let's summarize what we said. We're looking at the number of states accessible to a macroscopic system. This system has external constraints. It's isolated system. Total energy is fixed, and its energy levels are determined by the external constraints, such as the external magnetic field. We call capital E total energy of the system, omega number of accessible states with energies in the range E to E plus delta E, where delta E is a macroscopically small, microscopically large energy interval, so that we have many states and energy can still be considered as a continuous variable. The density of states, rho of E, is number of states per unit energy range at the given energy E. Capital phi of E is total number of states with energies less than capital E. F is number of degrees of freedom. Total number of quantum numbers you have to specify in order to describe the state of the system. Epsilon is the contribution to total energy E from each quantum number, and lowercase phi as a function of epsilon is total number of possible values of a quantum number when its associated energy is less than epsilon. We called E0 ground state total energy, epsilon 0 minimum possible contribution to total energy from a quantum number. Now, the number of accessible states at the energy range E to E plus delta E is number of states per energy, density of states, multiplied by the energy interval delta E, where the number of the density of states is the derivative of total number of states for energies less than E with respect to the energy interval dE. So for a small energy interval delta E, this is phi at E plus delta E minus phi at E divided by delta E. So this is the derivative of phi with respect to E. That's the second relationship. And third, what are the possible values of a quantum number when its associated energy is less than epsilon? Well, if its associated energy is epsilon 0, it can only have one value, the minimum possible value. As we increase the energy contribution, possible energy contribution epsilon, the total number of values this quantum number can take will scale as epsilon minus epsilon 0 to some power alpha of the order of 1. The contribution to total energy from F quantum numbers, because each one has a contribution epsilon minus epsilon 0, is F times epsilon minus epsilon 0 is the total energy minus ground state energy. The total number of states for energies less than E is the total number of values the quantum number can have for energy contribution less than epsilon. And this is done F times because I have F quantum numbers. So it is lowercase phi to the power F, the fifth relationship. And if I substitute this for d phi dE, the density of states, I find that the density of states scales as total energy minus E0 divided by F to the power alpha F minus alpha, and so that the number of accessible states is E minus E0 divided by F to the power alpha F minus alpha. Then I note alpha was of the order of 1, F is of the order of Avogadro's number, so the number of accessible states is scaling with energy as E minus E0 to the power number of degrees of freedom. And the natural logarithm of the number of accessible states scales as the number of degrees of freedom F, provided that we are far enough from the ground state energy E0. That's our conclusion.